Yeah, thanks very much. So yeah, this is the second talk on the local geometry of the Ricci flow, at least various aspects of it. And just a reminder, we're looking at Ricci flows on smooth manifolds without boundary, maybe not complete. When we came down to the following situation, we noticed that we've got all these estimates on balls. If they're compactly contained in the solution for different times, and we've got bounds from below, say on the Ricci curvature, then we were able to show distance estimates. We explained that in the first talk. And furthermore, if we even assume that we have a bound like C0 on T from above, or maybe just Ricci less than or equal to n minus 1 C0 on T from above, then we could get some bounds also from below like this. So in the end, we ended up with these nice distance estimates in any general setting like this. And as I said, the completeness condition has sort of been removed now and replaced by the fact that the balls that we're considering are compactly contained in the solutions that we're looking at. So maybe we'll just write this one down for later. We're going to be using it quite a bit. So we've got the distance at time 0 minus some constant depending on n times square root of C0t. In our setting here is going to be less than or equal to dgt xy, and that's going to be less than or equal to, this is the nice direction here, this is a lot better control. In this direction we have a sort of Lipschitz continuity in this direction. In the other direction we just have a continuity in the metric. And this is in the case if we've got these balls of, say, radius. I'll just give an example here, say 5, with respect to the evolving metric around some fixed middle point, and they're compactly contained in the solution for the times that we're considering. And we're assuming, as I said, Ricci bigger than or equal to minus n minus 1 times k, or Riem less than or equal to, let's just take Ricci bounded from above by C0 n minus 1 on T. Okay, and then we only get these estimates then for some fixed time depending on all the constants that are coming up here. In this case we've got C0 and what else have we got? K is our lower bound. And here, as I said, we need to be careful. We only get these distance estimates for points which are well inside, far enough inside the balls we're considering. So we really want to take, in this instance here, for example, I took a radius ball 5. So we can only get these things to work because we're going to be looking at curves and geodesics which live in that space. And once we're in this situation, the argument is, as I said, essentially the one I gave before without really any major differences. Okay, so this is the setup we've got. We need quite a few things before we can get the local estimates which we want. So let's just go to one of the lemmas that we're going to require. Well, this one here is a similar one to the one that I looked at in the two-dimensional case where we showed that the scalar curvature is remaining bounded from below by, say, minus 1 for a short time. So we had a condition, Ricci or scalar curvature. We already knew it was bounded. And we have volume at time 0. Now everything's being localized now, so I'm assuming at time 0 on a ball of radius 1, we've got V0. And here the Ricci condition, now I'm just assuming that I've got it on this thing here. Once again, all of them compactly contained in M for each time. Then what we're going to get is just in the way we did it before for the in the case of the two-dimension and the scalar curvature case, we really don't need to change the argument much. We get this bound like C0 on T for the curvature, for the full curvature tensor now. So to get this, we need to do a similar argument to the one we did before. Of course, there are a few minor new ingredients, so I better mention what those are. So one of them is, before we were on a compact manifold, so we could just do a blow-up argument. Now we need to do a bit more careful. We've got to stay within the ball when we're trying to find these contradiction points, right? So we just do the the so-called Perelman point-picking argument, as Chi Wei explained or considered in a talk he was looking at and other people have considered. So we need to do that in place of just this contradiction argument. We need to be a bit careful that the points are staying within the ball. So we're getting this on a smaller ball. We've got to make sure that we don't go outside. And that's one ingredient. So that's one change. Now you remember we had the evolution of the volume in terms of the Euler characteristic and the initial volume bounded. By the way, because the Euler characteristic has a bound from above, you could get rid of the Euler characteristic in the constant I had there, and you just get a bound from below on the volume. Now we've localized to the situation. So how are we going to get this volume control? How do we get that the volume of balls is not collapsing too quickly, which was part of this argument here? Remember, we used Bishop Gromov, and we used the fact that we had control of the volume ratio of balls. So the question is, how do we get this? How do we make sure this doesn't happen? Well, we only want all of these things for a short, well-controlled time interval. So the trick is you say, well, for some time this is going to be true for some short time, and you now get a control on the time for which this is true, and then everything else goes through. So how do you get this control on the time? Well, there are various ways of doing this. So plus volume control for short time. Okay, there are various ways of doing this. So I think the one that most people are familiar with is that if you look at these estimates up here on the distance, you see that distance is not changing too quickly. You have control over how quickly distance is changing. So you could use Cheeger coding. Cheeger coding says that if you have control on distance and a bound on Ricci from below, then you get volume convergence. So you can use a contradiction argument to show, well, this can't go down too quickly. If it's at time 0 something, then it can't drop down too quickly. So you could use this. So this is actually how I initially did this in the compact case, the theorem I wrote down before. But we were interested in this paper with Peter Topping, we were interested in trying to giving a new proof of this non-collapsing result here, which didn't use Cheeger coding. And the idea was as follows: why didn't we use Cheeger coding? We're hoping in the future that there are other situations where we can apply this result to, where we might be in a more general situation when we don't necessarily have this. So we're trying to make sure that we can use this result in the future. And the other another interesting fact about the way we show this without using Cheeger coding is that the proof is really kind of just using quite basic things. So it's using Bishop-Gromov comparison principle, counting of balls, so in a simple sort of way, and the fact, well, I said some simple things, also the fact that for smooth manifolds with Ricci curvature bigger than or equal to 0 and bounded curvature, you have splitting type theorems. So we just reduced a lot of the arguments to these, what I call simple. They obviously have important theorems and names behind them, but nevertheless it's things that people are quite familiar with, and we hope that these will be useful in other situations. Anyway, you can take your pick how you want to control volume. Either use Cheeger coding and the distance estimates, which we have already got, or this other proof, which you can, like I said, it just uses these ingredients. Okay, so we'll need this local estimate in the end to get our results. So this is the idea, and I've given you the main ideas. There's one other ingredient. This was mentioned in Peng Lu's talk. Of course, we need to be a little careful here, because when we do our contradiction argument, in the end, all we're going to get is something with Ricci bigger than or equal to 0, an ancient solution with Ricci bigger than or equal to 0. Now, there's a fact that any ancient solution with bounded curvature is in 3 dimensions. So you notice here we're sticking with 3 dimensions, and non-negative asymptotic volume ratio has got to be, or positive, sorry, I'll say that again. The only solutions with positive asymptotic volume ratio and bounded curvature and in 3 dimension and ancient are actually all isometric to Rn. So this is a fact proven in a very general situation by Binglong Chen, and actually proved in the case of bounded curvature. So Binglong Chen proved this for any solution without necessarily bounded curvature. But the bounded curvature case was proved independently by Ben Chow and Dan Knopf. So there are 2 ways of seeing this. So now we've got all the ingredients. So I'll just write plus Perelman's singularity theorem, but in fact, you've got to be a little bit careful, because what I'm using, I didn't say this completely correctly. I said it correctly, but I'm missing out a point. Any ancient solution has sectional curvature bigger than or equal to 0 in the setting I just said, and then you can use Perelman's singularity theorem. Right, so this is what was shown in these papers I mentioned. So you're able then to just follow the procedure I did before. So essentially you just do the same thing, a blow-up argument with a point-picking argument, and all these ingredients slightly modified to get your claim that this is the case, and also now we see that this one here is the case too. So we've managed now to get a sort of more local version, and notice that this is very specific to 3D, because I use this fact that if you blow up and you get an ancient solution, which is in 3D, then this thing is going to have sectional curvature bigger than or equal to 0 in the setting that I'm looking at.
In the singularity argument,
yes.
you can say that the scalar curvature is positive after the blow-up argument.
Non-negative. Non-negative.
Non-negative.
Yes.
But how do you get the non-negative from the...
Oh, that's what I just said. So the point is that the blow-up argument gives you an ancient solution. And once you have an ancient solution in 3D with, say, non-negative asymptotic volume ratio, it's got to have non-negative sectional curvature. So this is the result that Binglong Chen showed, and I said also Dan Knopf and Chow proved it in the case of bounded curvature.
Where is the contradiction?
Well, then the contradiction's just Perelman's singularity theorem again, because I have non-negative asymptotic volume ratio, positive asymptotic volume ratio, and Perelman says that has to be isometric to Rn, in this case R3, the standard one, but I did the blow-up argument so that the curvature is equal to 1 at some point. So it's essentially exactly the same as before, but we need to get into the situation that the sectional curvature is bigger than or equal to 0, and that's how we need to use these theorems, and that's specific to the 3-dimensional situation. Right. Okay, so we can prove this local result, and we get the information that we require. Right, what other things do we need? Well, we're localizing. So at the moment, we're just collecting the local lemmas, which we're all going to put together in the end. So another important feature is these so-called Perelman cutoff functions. So Perelman introduced these cutoff functions in specific situations, and we've just sort of written everything down for this special situation that we're looking at, and written down the properties of these cutoff functions that we need. So we don't have bounded curvature. Later we're going to be interested in the case that we have curvature like C0 on T. So what we want to do is, even in this case here, by the way, notice I have no bound from below on curvature or anything like that. So this is very kind of general situation. Just Ricci less than or equal to C0 n minus 1 on T. Nothing else. Once again, the balls are compactly contained in the M you're looking at. Then you can construct these cutoff functions, I call them H, which have these nice properties. So the most important is that ddt of H is less than or equal to Laplace GH. So it's a subsolution of the heat equation. They're almost on the small ball, so you want to cut into a ball of radius R1, which is smaller than radius R2. R1 is bigger than radius R2. On the R1, you want it to be 1, but you have to go in you have to change it a little tiny amount. I mean, for t equals to 0, it is 1, but here it's just going in a slight amount from 1. Further in, it's equal to 0, and of course, like a cutoff function, it's remaining in 0 up to e minus kt, and it's satisfying this information here. So this is, as I said, I make this clear, this is Perelman's idea how to construct these cutoff functions. People are using cutoff functions like this in all sorts of places with Ricci flow now. So the trick is that you just, in the setting that I look at here, what you do is you take your favorite cutoff function in Rn, so you call it eta, which has the properties of a usual cutoff function on a ball of, say, radius r1 and r2 in Euclidean space, and then you just take this function here. You need to take a m here, where m is just going to be equal to something which is depending on this C0 and n, which I've got here. And if you do this, the important thing is that Perelman showed that this has a very nice quality, satisfies a very nice inequality. That's where you get this thing here from. And you're using a cutoff function which is in the usual situation in Rn, so it's decreasing and it's controlled and so on. So this is a nice situation. So here would be my R, what have I called them? R1 and R2. So we want R2's less than R1, so here's an R1. So we've got this situation here. Now you notice that I've put in some other extra information which we checked, which we need actually. In fact, so this is satisfied in the barrier sense. And, this should be gradient of h, not gradient little h there. The gradient of this function here is actually bounded by h to the 1 minus epsilon for any epsilon bigger than 0. So this is a usual fact about cutoff functions. You can go as close as you like up to 1 just by being a bit careful, but this v is going to get worse and worse as you do that. Now usually the one you're used to, I'm sure, is when you have gradient h squared is less than equal to vh, for example. This is the standard one. This one's just a little bit finer, which is required actually in the proof that we give. So we need more than just the usual estimate that people have. But you can always get this for a cutoff function just by increasing the power of the cutoff function. So most of you are aware of this, but it's a nice fact, and I've just written it down here so we know that I'm really going to need this little extra bit. And that just comes from this property here on the fact that the gradient of d is equal, the norm of the gradient of d is equal to 1. Okay, and this is in the barrier sense. Okay, so there could be places where they're not smooth, but you can always construct a nice approximating function which satisfies similar inequalities. Okay, so now we're in a situation where we can prove the case for n is equal to 2. Right? We've got the estimates for n is equal to 2. We're actually in business. So for n is equal to 3, we're not in business. We haven't got enough. But let's just, because the n equals 2 situation is sort of illustrative, so maybe I'll just explain how we do it. The n equals 2 local situation. What you do now is, well, you say we've got, so the scalar curvature at time 0 bigger than or equal to -1, say on a big ball, say radius 5. And you want to show that for what you're trying to do is show that the scalar curvature at later times is, say, bigger than or equal to -2 on a smaller ball. Let's say here with a 2 in here, yeah, that's fine. And we're assuming these things, I'm going to assume they're compactly contained in there. And you want to find some time interval for which this is holding. And we've also want to get that the volume of, say, the ball of radius 1 is not collapsing too quickly. Call it epsilon 0. If we know here, the initial condition, of course, is that the volume at time 0 of this thing is, say, bigger than or equal to V0. Okay, so that's the setting we've got. And, well, how are we going to get this? What we're going to do is show, well, for a short amount of time, we know without any problem here, this is scalar curvature here also, because it's just curvature, there must be some C0 on T, so that if I go in quite a way, say now I'm going into 1, or let's go right into a half even, doesn't really matter. you've got this information here, right? So the idea is you've got this for some time interval, all these inequalities here, and you want to show that they remain true for a well-defined time interval just depending on this initial value here. Right, in this case it's just V0. It's the only thing that's coming up. We want to show that T max, is bigger than or equal to some constant which just depends on V0 and is bigger than 0. So the idea is, I should point out that Binglong Chen looked at this situation in the case of bounded scalar curvature, and he also considered a similar procedure by looking at the cutoff function by the scalar curvature. He could show a pseudo-locality result in the case that the scalar curvature is bounded in a region. So we do a similar procedure here in that we just times by our scalar curvature by this special cutoff function in our setting. So we've got all these properties, and you just look at the evolution equation of this. What do you get? Well, you get the usual one here. You're getting an error term from the cutoff function plus 2 times eta Ricci squared, but we know that's just scalar curvature squared in the setting that we're looking at. Okay, so things are looking pretty good except for this term here. But in the scalar curvature case, this term turns out to be no problem at all, because what you do is just do a standard sort of tricks. You write the scalar curvature as the scalar curvature times eta at a first time where this thing, say, is equal to minus 3/2. So we want to show, should have pointed this out, we're trying to show that eta times r is bigger than or equal to, say, minus 3/2 on the whole ball now. Okay, if we've got it at time 0, then it must be true for a short time, and we're trying to work out what happens at a time when this is violated, so it's equal to minus 3/2. Then in any case, eta is not 0 at that case, so you can do this standard trick where you just bring the eta in, and then of course you're getting an error term here. And we've got this eta r squared term. Okay, so now actually this situation's, as I said, quite a lot easier, because what you've got is, well, let's do it this way. I can write this as, say, 3/2, and then I can put an eta to the half here, and put it around like that. Now remember, I told you these cutoff functions that's bounded. I'm still not up to, the bad situation would be if I went right up to 2. So this is bounded by a constant, bigger than or equal to now some constant, which is depending on 3/2. I'll just write it as c. Now we've got r eta to the half plus eta r squared. So we can just use Young's inequality. At the time where this thing finally reaches 3/2, that's a minimum, that's 0. So you get Laplacian eta times r minus a constant plus something which is actually, we can take a half even and still have this. Just using Young's inequality. Put a c squared, it's just some new constant. But this constant is just depending on, it's just a universal constant. And so we see now by integrating that in fact for a short time, eta r is never going to be equal to minus 3/2, right? This is a sort of standard argument. You see there's a slight little change here. We need a little bit more control on this thing, and then we get our estimate. So we see this is not going to be violated either for a well-defined time interval as long as everything else is not violated. Right? But this was the one problem. All the other lemmas say as long as we've got this far enough in, then we've got everything else, and we've got our cutoff function, so nothing goes wrong. Right? This is the nice thing. Now notice, by the way, there's one slight thing I'm not spending too much time explaining, and that's this fact here. You only need your bound on the curvature on a very, very small ball inside. So that's why I'm saying as long as we've got it here, we could get this cutoff function. So I've gone a long way in from the ball radius 5 or 2 or 1. So we can really construct these cutoff functions without any worry. So that turns out to be the argument for n is equal to 2. Right, so the question is, what happens in n is equal to 3? So the 3D case, we can't do this. 3D case is no good. can't just argue this way. This argument doesn't work. Well, at least we can't. We haven't got it to work in this way at the moment. Maybe there's some modification, but we tried many modifications. So your first bet might be, instead of looking at eta times r, you're interested in the Ricci curvature. So you try the same argument with eta times Ricci. Okay, that didn't work. Then you try adding in some constants, some things which you know you've got control over. So you add in a constant times scalar curvature t. If you don't have this cutoff function here, this is exactly the function that I used, or the tensor I used times the metric, of course, to prove that Ricci curvature remains controlled for a short time in the three-dimensional case and the global case. So you might think, okay, we just try a cutoff function, or maybe even take the cutoff function here and so on. You can start trying other things, adding in things. And anyway, this doesn't work. Okay, there's always a problem that comes up. And as a result, we can't just immediately do this argument like this. So that's I don't think it's bad news, it's just the news. So what have you got to do? You have to prove a new lemma. And the first lemma we want to prove is that if you know that your, so here's the 2D case I just proved. So here's the 3D lemma we need now, sorry. Let's have a look, here it is, right. So what you've got to do is you've got to introduce a new lemma and bring in a new argument. Okay, so the new lemma is maybe not too surprising, but the new argument is something which needs to see that it works. And by the way, the new lemma here also needed some new ideas. Okay, so what's the situation here? The situation is, once again, we've got some nice balls which are compactly contained in M for the solutions you're looking at. No, I'm not I'm pressing the top, but this is the 3. Yeah, sorry. Yeah, it keeps going back. I see. Thank you. Yeah, all right, maybe I'll just point with my finger because it keeps jumping. So we've got this thing. We've got the Ricci big equal to minus k at time 0, and we're only on this ball, scared to use this pointer, at time 0 there. And we've got, at later times, we're compactly contained. And these are all things of time 1. And now you're going to assume that you're right on the whole ball, that you've got curvature control. Right? So somehow we don't want to do that. We want to kind of show that, on other things. This is why we need to assume it on the whole ball now. In this case here, we saw it was enough just to have it on a ball way inside. So this looks like a bit of a problem. We'll see in a moment why it turns out not to be a problem. Anyway, the local lemma that we managed to prove is that if you have everything on the whole ball of radius 1, right, so you need this on the whole ball, then you can get your bound on the Ricci curvature from below in terms of the constants involved here. Now, an interesting feature of this is that, notice, by the way, there could, at least in the proof, there could be a jump. In the sectional curvature, you only go down continuously with time. Here, at least in the proof at the moment, there could be a jump. So I'm not sure if this is a relic of the proof or if this is really something that could happen. So I'm not sure about this. Anyway, it's in both the global case and the local case, it turns out to be the case. And of course, you only get it on a smaller ball, right? So you assume at time 0, bigger than or equal to minus k, and C on t control on a ball of radius 1, and you get this thing here. So I'm not going to present all the details of the proof here because that's one of the main parts of the paper, but I'd like to focus on where there was where we needed a new idea, okay, and what actually turned out to be sort of interesting was, well, instead of looking at this quantity here, and now, like I said, we have to assume C on t behavior, you have to introduce a new quantity, and you have to do it in 2 steps. You saw here we got 1 step, we managed to show it. Now we needed 2 steps. We needed a double bootstrap argument to show, in fact, that the Ricci remains bounded from below. So let's introduce the tensor that we need. Well, we've got our cutoff function from before. So what you do is you define a new tensor. The first part is, well, no big surprise, Ricci xt. The next part is also maybe no big surprise initially when I write it like that, but we need to change the power here. Alpha is going to be bigger than 1 and less than 1 to give you even more power in this argument. And the next thing you need is a small t to the epsilon. Now we need plus 7k times g. Now if you do all of this, you use this one here, then you can use a maximum principal type argument with this quantity here to get this. And okay, the bad term that comes up here, if you forget this here, everything's quite nice. The zero order terms manage to get cancelled by these good terms here, as they did in the global case. So why do we need to introduce these things here? And we actually choose specific values of epsilon. Epsilon's also, by the way, very small. We choose explicit values, but why do we need to introduce this? It's to take care of the bad error term. The bad error term, before we took care of it pretty easily with the scalar curvature case, remember, was this term like this. This was the error term. Now, of course, we're going to have a Ricci coming in. Right, this is going to be the bad error term that we've got to get control over. And, well, the first thing you could try, just like we did before, do the same sort of analysis and say, well, I sneak in this epsilon, and that's exactly what we do. So this is going to be 0 at the place where you're interested in. And then you get following term. Let's see. Scalar curvature, right. So we've got this scalar. There's a term coming in like the scalar curvature. I think I've made a slight mistake here. Yeah, that's just a gradient. Right, so you see here what we do is we let this equal to, remember here's our tensor, so the term we're getting is like an r. That's going to come here, a gradient r, so I'm missing that too, sorry. And we're getting a t to the alpha, and we're getting this 8k. So that's the new error term. Okay? Now if you look at this error term, you think at first this is not going to work, right? I mean, this is exactly the wrong power of the thing that you want. Gradient eta on eta is exactly where things blow up. If I had 1 minus epsilon, I'm okay. But this is exactly wrong. And you then look at this and say, and also there's another term coming from gradient r. So this is going to give you another bad term, which is out of control, right? But we remember that this is almost good. So let's write it like this. Okay. This one's controlled by a constant. So we got rid of one bad term. Using Xi's estimates, that's why we need to go assume curvature is less than or equal to C0 on T on the whole ball. Using Xi's estimates, you get a sort of T to the 3/2 terms here. Now it's looking a little bit better. It's still not quite integrable because you've got this term here. You don't know how to get control of it. Well, the trick is that at the first time when this thing is equal to 0, that's what we're looking at again, you can use the fact that the curvature is less than or equal to C on T. And if you write it down in this inequality here, you'll see that it means that eta's bigger than or equal to some constant times T. So it's not quite 0. And then you're saved, because you put this in, and you've just got a T to the epsilon times a big constant depending on epsilon now. Now, you see, what have we got? You've got this alpha minus 3/2 minus something really small. Just choose alpha, right, close enough to 0, and you're going to be able to, this is integrable then, right? So this term is going to be integrable. So this is I should have said alpha close enough to 1, and then this thing will be integrable. So it becomes integrable for nice choices of good choices of alpha near 1, say, for example, and small epsilon. Okay, so that's the main part. All the other terms are just sort of 0 order terms, which are, these terms take care of the evolution of the 0 order terms in the evolution equation I should say the reaction terms in the evolution equation of the Ricci curvature, and everything works out. This is the hard term, and that's I've given you the argument of how you take care of that. Right. Yes.
Originally, you said eta is sort of the bump function. But how come
Yes.
it becomes dependent on t? Because it's a bump function dependent on time.
Because, good question. So I said we're looking at a time, first time when this is 0. Okay, so assume that's equal to 0. And I'm using Ricci's less than equal to c on t. That means that's sort of like c on t. Times eta has got to be equal to this side here. Yeah? Right. Yeah. So it turns out that you do have a surprising information at the time you're interested, only at the time where things go wrong. Right. Yeah. Right. So this was then, good news, because then you say, well, okay, so this will show you that the Ricci curvature is bounded from below by this quantity. This is like c on t. This is not quite t to the 1, so you get something integrable in time. So it shows you Ricci is bigger than or equal to minus c times t to some power, which is integrable. And so you started to make progress. Then that's the first step in the double bootstrap procedure. In the next step, of course, you use this to actually show, you go through the argument again, and now you choose alpha is equal to 1, and you can actually show then that the Ricci curvature does remain bounded from below. And you can get, like I say, the control with some sort of slight jump, but you've still got control. Okay, so in the last 5 minutes, I'll give you the idea of the proof of a theorem we're trying to prove. So here's what we want to prove at the moment. We want to show in the three-dimensional case that we do really have a very local situation. Okay. Right. You see, okay, I'm assuming BC. I'll explain why we assume that. But other than that, volume bigger than or equal to V0 at time 0, Ricci bigger than or equal to minus K. The usual condition that you're going to assume your balls of the radius you're looking at are compactly contained in the thing that you're in the manifold. Then you're getting this information here. Volume bigger than or equal to V0 bigger than 0. Ricci bigger than or equal to minus K tilde for some K tilde depending on the solution, and Riem less than or equal to C0 on T. So let me just try and give a brief idea about how you're going to get this. Because we've got all these local lemmas, but how do we put them all together? So, yeah. Is there any way of getting this screen up now? You just push it. Okay, yeah. Right, so let's see now. What you've got is you're trying to show this on this here, the initial assumptions was, say, on a bigger ball, and you have to go in a little bit. So you're trying to, what you really want to show is that this estimate's happening. So you're assuming, I'm going to draw a slightly different picture. Here's your point, and you've got a ball, and you know here, say Ricci's bigger than or equal to minus 1 times 0, and volume of this ball is bigger than or equal to V0. That's the situation you've got. And now what you want to show is, the missing estimate is that you want to show that if you go in a little bit, you're going to get control after looking at this situation. So here we're going in 1 minus, and now I'm going to have to take some constant. I'm just going to call it L here. It's something really big. In the paper we give an explicit L here, but let's just, for the sake of explaining the argument, say it's going to be something very large, just depending on this V0. So I've removed K from here, and I just want to stick to the V0 situation so that we know how to do this. Once we get this, by the way, then we're done, because then we can just use our local estimates to show that Ricci is also bigger than or equal to some constant on a slightly smaller ball. And this is, of course, for all t, say, less than or equal to 1 on L. So this is a very small time interval. So what you do is, to get this, you blow up. You assume this goes wrong at some stage. Then you blow the situation up, and after writing it down correctly, you see that you can always kind of look into this situation here. So now your x0 is now way off here. And what you're interested in is sort of, I'm going to draw it like this. This is my time, but it's actually square root of time. And this here is the distance to x0. So what you're interested in is, so you've got this time and point where the curvature finally hits C0 on T0. Okay, and before that, everything down here inside the ball, so we're a long way off from x0 after scaling, because your times are very small. Before that, what you've got is curvature less than or equal to C on T at the time you're interested in. At any times in there, and any points you've got that. So there's a first time where it goes wrong. So you've got two situations. So this sort of blow-up argument usually doesn't work. Okay, if you do a blow-up argument like I'm trying to now, it will generally not work. So something's got to be here helping us. Yeah, what's going to help us? Well, it's this local property of the Ricci flow. Right? So once again, it's all coming back to pseudo-locality and the local properties. Well, let's assume the point's kind of not too bad. So it's a fair way in. These distances are getting huge when you scale, because you're only interested in really small times. And this thing here is very, very steep here. So I should say very, very shallow. Right? So the times where things can go wrong are going to be, either close to 1 or a fair distance away from time 1. So let's just look at this situation here at first. If you're in this situation, so I'm just drawing everything as if it's sort of like a Cartesian product, right? Of course, the balls are changing and moving around in space, but that's not a problem because we've got control about how they're behaving due to these balls limits, the distance control fact. So I'll just draw it as if everything's just a Cartesian product, and then say we just use the distance estimates to really get into the situation. Now, if you've got enough room here, so you're far enough away from time 1, you find a big space-time cylinder where this is the case. Now, because you scaled a huge amount, you're having here Ricci at time 0 is really small. Epsilon 0 is a very, very small number. Okay, it's a scaling. I'm just doing a scaling argument. I'm assuming L is extremely large, and that means if you're away from time 1, then you've got this really extremely large, small Ricci curvature, lower bound, and you've got this very large region inside here, this space-time cylinder going right up to here. Now, what you do is you say, well, this is a small C0. I've said there's got to be some C0. So you take this small C0 equal to the big C0 you had before, which came from the local lemma. The big C0 was the fact that as long as you're in this nice sort of situation, you've got Ricci being equal to minus epsilon at time 0, and you've got some sort of bound, that improves. First of all, you get the double bootstrap lemma tells you that you've got Ricci on this whole region now, bigger than or equal to, say, some big constant times epsilon 0, but that's still extremely small. So not the local lemma. Sometimes get this wrong. The double bootstrap's the one I just did before, tells you this. On this whole region, once you go in a little bit. But you've still got a huge cylinder now where you have extremely good bound of curvature. So now you use the local lemma, and that tells you that the curvature is actually less than or equal to this big C0 on T. But big C0 is way, way less than little C0. So this couldn't have happened. You can't have reached little C0 divided by T. So you get a contradiction. So that would be fine, except this is not usually the case. The dangerous case is that, so this is how you just use the lemmas if this Y0, T0, the time where something goes wrong is a little bit away from 1. The dangerous case is exactly the opposite. y0, t0 is somewhere like this, right? Now it looks like, okay, we've got no chance, right? We're done for. So what do you do? Well, there's one extra ingredient you do. The first thing you do is you can say, well, I can go way up with a huge space-time cylinder, at least up to time this special fixed epsilon 0. I can go way up to here and do the same argument. Same argument. So you're getting, what are we getting? We're getting this inequality here. So we're getting on a smaller but still huge here, right up here, we're getting Ricci bigger than or equal to minus k times epsilon 0, but epsilon 0 is tiny. So this thing here, I think I said k was 1 anyway, so it's a minus 100 times epsilon 0, which is still tiny. Sorry, I should have put this is the correct constant here, sorry. So you're still tiny in this whole region here. Now, what you can do is say, well, let's start here now. I can do Perelman pseudolocality to get C on T control in here. So I can get more C on T control a bit further up, but some other C on T. But no problem, you use now the double bootstrap lemma again, and you'll see that Ricci's very small in there, and that you've got your usual big C0 on T behavior. So that also implies, in the second case, after using Perelman to just go up a little bit further and to get out of the cylinder, to get out of this sort of this mountain here, you also get a contradiction, right? You get that actually curvature is less than equal to this big C0 on T. That gives you your contradiction, and that finishes the theorem. Right, that's all I wanted to say. Thanks for your attention. Yeah.
You have a gradient edge defined by v times the edge to the power 1 minus epsilon.
Yes.
I think this is an improvement of Perelman.
This is, okay, so the first thing is just to get, that part's not really much of a difference, because all you have to do, if your original cutoff function is eta and then you have dt and so on in there, okay, just change this eta to a high power. P for extremely high power, and you'll see that it satisfies this. So, right, it's something that's not often used, but if it's it's not complicated. You get then just write down, differentiate, and you get p minus 1 and so on, and it turns out you're getting, that's where the v comes from. This high power of the p's comes into the v, but in the end you still get better control of the test function, and it's in this argument here, it's extremely useful and important. Yeah.
Bias